This video is going to look at work and power, which, as we've defined, is how we actually change the energy of something, how we change how much energy is in an energy system. So jumping into it, work. Work is a transfer of energy using force. So if there's a force acting on something and it's causing the energy to change, that's what we call work. So work is equal to force times, or a parallel force times a change in position. So in other words, if I push something for a given distance, I will do work on that object. And these need to be parallel. So the direction of the force needs to be parallel to the direction of motion. So I push something to the right for a certain distance as I move to the right, then I'll do work on it. If I push something to the right while it's moving up and down, then I'm not doing work because these aren't parallel, they're perpendicular. And you'll notice these energy, or these units, are the same on both sides. Work has a unit of 1 kilogram meter squared per second squared. That's a unit of joule. And that's going to equal a Newton times a meter, which is also equal to a kilogram meter per second squared times a meter. A Newton is a kilogram meter per second squared. A meter is a meter, so multiplying them, we get the same thing on both sides. So now we want to talk about the way we phrase things with this. So if I say an object does work, that means it's losing energy exerting a force on another object. Its delta E should be negative. So if an object is pushing something else and doing work on that other object, this first object is losing energy. An object has work done on it when it gains energy because another object is exerting a force on it. So if something does work on me, I'm gaining energy because a force is pushing me over a certain distance. We can also, again, write it like this. So the amount of energy change is negative, the amount of energy change is positive. Or in other words, the work is negative and the work, well, that's not a good way of phrasing it because that gets a little ambiguous and it's not one-to-one how we describe them. Let's jump into an example which should help show how this comes into play. You're pushing a box up a ramp with a force of 50 newtons. If the ramp has a length of 1.5 meters, how much work do you do pushing the box? And it doesn't say it explicitly here, but we're treating it as if you're pushing parallel to the ramp. So if the ramp is like this, and you're pushing with a force like that, so they're parallel to the distance that the box moves. So we know that work is equal to force parallel times delta x. In this case, we know that the force is equal to 50 newtons, and that the box is going to move a delta x equal to 1.5 meters up this ramp. So work is equal to, these are parallel, so that's great, force, and we know that the delta x is going to be to the right. I don't need to write force. We can do 50 newtons times 1.5 meters. Work is equal to, that should be 75 Newton meters, or also 75 joules. Sometimes you'll see work presented as Newton meters. You can do that or as joules. Now note that we do need to care about direction. These are both pointing in the same direction, which is why the work done is positive. The same box slides back down the ramp, losing 30 joules of energy in the process. If it's losing energy because it is doing work on the ramp through the frictional force, what is the frictional force between the box and the ramp? So now we have the box sliding down the ramp. And we're going to assume it slides that same distance of delta x equals negative 1.5 meters. And there's some unknown frictional force up the ramp. So now we know that work should equal force parallel times delta x. We know the force should be in the positive direction, so we expect this to be a positive value. The delta x we expect to be negative. Work over delta x equals force parallel. Work, it's losing 30 joules, so we need to say negative 30 joules. Delta x is negative 1.5 meters. And that should equal my force parallel. 30 over 1.5 is 20. And joules is a kilogram meter squared per second squared. This ends up with units of newtons when I divide those out. So in other words, the box has a frictional force of 20 newtons. And that was just from knowing how much energy was lost, knowing the distance that it was displaced. That lets us calculate the average force here. Next, we're going to talk about power to close out here. Power is the rate of work being done over time, or in other words, the rate of change of energy being done over time. So power is equal to work divided by delta T, or it's also equal to change in energy over delta T, just because remember work is equal to a change in energy. Power is measured in watts, which we write as 1 W, and 1 watt equals 1 joule per second, which makes sense if you look at our units up here. Work is a W, or work is in joules. Change in energy in joules, times is in seconds, so this is our units here.